Okay, so last time we left off at, I think, the start of the boost converter, the step up or boost converter, correct? So we sized up the capacitor, including ESR, the equivalent series resistance of a capacitor, and we saw the effect of that, right? So what was the effect of that we saw last time? What was the effect of that on the output voltage ripple? No, the ESR of the capacitor. What do you mean translates the voltage? So I mean, just look at the circuit, right? So your calculations were based on, okay, your calculations for voltage ripple before including this ESR were based on what? The fact that you have an ideal capacitance. And to calculate the value of the capacitance, you were calculating the area under the capacitor current curve, dividing that by your voltage spec, right? Your ripple voltage spec. And then you calculate capacitance. But now this was considering only an ideal capacitance, right? So now we don't have an ideal capacitance. We have a capacitor in series with a resistor. This is my actual physical capacitance. So you know how to deal with this. But how do you deal with the resistor? I mean, at the end of the day, I would like to calculate the voltage ripple across my capacitance. So how will this resistor affect the voltage ripple across these two terminals? Remember, capacitor current is AC, right? So it has an average value of 0. So that means I have an AC current coming in and out of this branch. What will that do to what will the voltage drop across my resistor look like? To look exactly like the current, scale with the value of the resistance, right? And then it will be what? Added to the capacitor voltage ripple, right? So it's going to increase the voltage ripple across my real capacitance. Does it make sense or not? I mean, you have two components in series. If you remove this resistor, there will be no voltage drop across it, right? You have this resistor in place, and you have current flowing in and out. What will that do? That will cause some voltage drop. This voltage drop will be added to the voltage drop across the capacitor. I mean, you have now the capacitor voltage ripple will include the ripple due to the ideal capacitance effect, as well as the ripple due to the fact that you have a voltage drop across a resistor. Right? So you're adding these two together. These two voltages are being added together. Yes? No? And we looked at a daily sheet last time for capacitors, and we saw that they clearly list ESR, for example. They would list ESR here they list it at 120 hertz. Can somebody think of why they would list it at 120 hertz? So ESR would change with frequency, okay? Because again, this capacitor is a wound component, and will have some. I mean, the equivalent circuit, where I mean, it's actually the equivalent circuit of the capacitor is not pure C and then an ideal and a resistor in series as well. There's some equivalent circuits will include actually inductors and parallel combination, and they would have some funky characteristics, and these all depend on the value of frequency. But why would they include the value of frequency here? Why do you think it's important? Yeah, in an application like in an electrolytic capacitor, this is an electrolytic capacitor data sheet. That electrolytic capacitors, we said they typically give us large capacitance values, and we said they're very poor with ESR, so they have a very high ESR value, and they give you here the ESR at 120 hertz. Why would that be important? Think of rectifiers, right? If you think of a rectifier, a 60 hertz rectifier, right? What was the full wave output frequency? You know, the input frequency was 60 hertz. The output of a full wave rectifier looks like what? Double the frequency, right? These two humps that double the frequency. So they're at 120 hertz. So they are, this capacitor is mainly going to be probably used in a full wave rectifier application, and in that application it is charging and discharging at this double the frequency of the input waveform. So if the input waveform is about 50 or 60 hertz, then the output is the capacitor is operating at about 120 hertz, right? Every 120 hertz, it's being charged, right? Charge, discharge, charge, discharge, charge, discharge. So that's why they would give you the. I mean, that's why they gave it to you here. Fine. If you're using this capacitor in a 10 kilohertz switching frequency power supply, you probably will not get good results with this number. This is not very useful. You probably need to go to the maybe the data sheet will have now ESR curves later or something. If not, then maybe this capacitor would best be used for low frequency applications, because maybe if you go to higher frequency, the ESR would be just significant. I mean, look at this ESR of 1 ohm here. For the 220 microfarad family at 400 volt DC, it's a 1 ohm resistor almost. Right? Here it's 1.92 ohm resistor. Right? So you probably don't want to put a 2 ohm resistor in series with a capacitor when you're putting in, again, 2 ohms. If you have 1 amp capacitor current, then you're talking about a 2 volt ripple, just because of the ESR. Right? Then you have to do the capacitor. Then you have to size the capacitor to make sure that you are. That means the minimum ESR that you can have, the minimum voltage ripple is going to be 2 volts at that current. That's assuming you have an infinite capacitor, right? If infinite capacitance, it means there is no contribution from ripple to the due to the capacitance. So if you have an infinite capacitance, you have a 2 volt ripple. Right? That's huge. That's a significant amount. Unless you're talking about maybe a power supply that's 10 kilovolts or something like that, right? Then 2 volts is a small amount, right? So it's application dependent, very application dependent. Yeah.
So
Yes.
what would be such a capacitor that would have such a high ESR?
Again, as an example, I said that these rectifiers may be something that you can tolerate. I mean, a lot of these front-end rectifiers, they're going to convert everything to DC. Typically, you will convert something to DC, and then you will do like what we have in the project. Take that rectified waveform and then use a linear regulator, or take that rectified waveform with ripple and then convert it to a higher, different voltage, different DC voltage, right? So take that 18 volt with ripple and convert it to 5 volts with less ripple using a switching power supply after that, right? So that's typically maybe where you would use an application, something like that. Yeah. The benefit of these things is that they can go to very large capacitance values. Yeah. Right, so it's high voltages. You can go to high voltages at large capacitance values. That's the benefit of these electrolytic capacitors. Yeah. So, for example, ceramics you'd never find a 680 microfarad ceramic capacitor at 350 volts. You would not.
But I read somewhere that ceramics are much more reliable, just
Sure.
in terms of lifetime and everything. So
Okay.
is there a preferred capacitor?
Because of ESR, right?
Right.
Lifetime, it depends on heat. Right, that's basically what it depends on. If you look at here, look at they will have I think lifetime or yeah, temperature ripple multipliers. I'm not exactly sure what this is, but I believe that this ripple multiplier is, the lower the temperature, the more ripple current or AC current that the capacitor will be able to tolerate. So for example, they give you the operating temperature of the capacitor minus 42 plus 85 degrees C. So there will be at 85 degrees C a maximum amount of ripple current, meaning AC current. Ripple here means AC current, because again, we know that capacitor current is always AC, right? It has a zero average value. So the amount of ripple current that can go through the capacitor at 85 degrees C has a certain limit. That is from these numbers in the numbers here on this side. They will tell you maximum ripple current at 120 hertz at 85 degrees C is 1.3 amp. Right? That's the amount of ripple current. 1.3 amp is that you can push through this capacitor. But if the temperature is lower, that the capacitor can withstand more losses, because again, ripple current, AC current flowing through a resistor inside the capacitor is going to cause local heat in the capacitor, right? So that pushes the capacitor temperature higher. Yeah. So that means that at 55 degrees C, you can tolerate 3 times more ripple current for this capacitor. At 65, 2.2, something like that. But why these are 255s, I don't know. I think this is probably a mistake. I think it's 55, 60, 65, 75, something like that. Right, they're exactly the same. I don't understand why. The other thing that they consider here is the frequency, right? So if you're operating at 120 hertz, the ripple multiplier is 1. So they allow you the certain value of ripple current at 120 hertz, which we saw in the list. At higher frequencies, they allow you higher ripple current. Why would they do that? Because you're pushing the frequency. What's going to happen to the ripple current due to the capacitor itself for higher frequency? You push the frequency, same waveform, but higher frequency. What's going to happen to the ripple voltage due to the capacitor? Why? Yes, to reduce, yes. Because from the equation, guys, right? It's the capacitor ripple is equal to capacitor size delta Q over delta V spec. This delta Q is the area under the current curve. If I increase the switching frequency, this area will be smaller. If I maintain the same duty cycle, but I increase switching frequency, this smaller area will be smaller. It means the capacitor that you could live with for the same ripple will be smaller. So if I maintain the same capacitance, I should be able to push in current with higher ripple into this capacitance. So higher ripple current. And that's what they have here. They multiply the ripple current by something higher. That doesn't help. It doesn't improve too much at the end of the day, because you're gonna at the end of the day be limited by the average power loss in the resistor ESR. It's inside the capacitor, so it's going to heat the capacitor anyway. So heat seems to be affecting capacitance a lot. If you look at here, you can push 3 times the ripple current at 55 degrees C, versus at 85 degrees C, the multiplier is 1, right? So all these things are important things to consider when you're designing a practical power supply. I think they also talk about, one interesting thing also is this. So the tolerance is plus minus 20%. So when you're designing a power supply, for these electrolytic capacitors, tolerance is 1 to plus minus 20%. So they're cheap. Higher capacitance can withstand voltage, but the tolerance that you're getting is to plus minus 20%. So you're asking for a 100 microfarad capacitor. Your minimum, based on what you're calculating, you're calculating a minimum value of capacitance, right? That minimum value of capacitance guarantees your ripple spec voltage. But these guys are telling you that this is plus minus 20%. So what do? You always have to jack it up, right? But at least you have a minimum point to start. How much you jack it up depends on your factors of safety. Right? So you definitely need to jack it up at least 20%, according to this. If you're not going to screen your components. If you screen your components, that's a different story, right? You can buy components and screen their values, right? In that case, you can always pick the ones that are exactly the required capacitance, but you're not going to do that in a production line, right? In a production line, you're going to buy from the vendor a big container of capacitors, and you're going to just keep installing them on the boards, right? So that's why they tell you the tolerance in their batch, for example. That's important. These are the most important things I wanted to talk about in this data sheet. I think there was one thing about the lifetime, but I don't see it. I don't know why. I can swear I remember seeing it before, but it was related to the temperature effect on lifetime. So I cannot see it. So it was related to temperature effect on the lifetime. So it's the lifetime of this capacitor at 85 degrees C is a certain amount. The lifetime of the same capacitor at 55 degrees C would be a different lifetime, right? So that's what I mean. The lifetime is something. It's also a spec, right? So it's something I wanted to touch upon here. Okay, back to the slides. So we went through this. So the total ripple now has to consider the ripple across, the total ripple is this delta V, 0, delta V output. It has to consider the capacitor voltage ripple, which we calculate from the delta Q over the delta V equation, and it has to consider the ESR, the voltage ripple due to the ESR, which is basically the peak-to-peak current, which is the delta I, the peak-to-peak capacitor current, multiplied by the ESR resistance. Okay? So that has to be your actual ripple spec now is this delta V0. It has to be less than the sum of these two. Okay? Which means that if you calculate based on your capacitance only, you definitely have to increase that because of the presence of ESR. Okay, so similar stuff happens for practical inductor selection. So I think with the data sheet that I have for the inductor on the website here, for example, do I have? No. No, I don't have the inductor data sheet. I have the magnetic cores and wire tables here. But you can choose an inductor based on the number. So we calculated the minimum value for inductance here based on, we looked at the ripple current and we saw equated the minimum current to 0. And from that equation, we calculated L minimum, right? And then you can definitely, and then anything above that will give you continuous conduction mode. Anything below that will be discontinuous conduction mode. You can take this L minimum and go to inductor vendors. There are vendors that sell inductors. They sell pre-wound inductors at certain values. They would sell you those, right? So you would go in with, you tell them I would like a certain inductance, and you would have to tell them what your peak current is. Why is peak current important? If you remember a BH curve for magnetic materials, the H, which was the magnetic field intensity, was proportional to Ni, was proportional number of turns times the current that's flowing through these turns. Yeah. So the BH curve looked, for a component that had a BH curve that looked something like this, you wanted a certain magnetic flux in the core, right? So you have a core with a certain cross section. This cross section of the core will only allow a certain amount of flux lines in a certain area. If you provide more flux lines into the core higher than what the material can tolerate or withstand, so there's a maximum flux density that you can push into this material, right? If you push more than that, what are you doing? You're not generating any more flux, right? This is current. You're increasing current this way to push more flux lines. This is proportional to the magnetomotive force, which is proportional to Ni, right? So if you keep pushing more current, you're not getting more flux lines being pushed into the core because the core has saturated already, right? So you typically want to operate in a region where your increases in current or decreases in current are changing the amount of flux in the core, so you are changing your component's value, if you would like, or the amount of flux or stored energy that you have. Otherwise, if you're operating here, you keep putting more current, you're burning current, also burning copper losses, and not getting any additional flux for that, right? So you want to operate at a certain flux density, for example, then you operate at a level where, okay, putting this amount of current guarantees a certain flux density. How about if you operate here? If you operate here versus here, you didn't get too much more flux density maybe, but you maybe got too much more copper loss, right? So it's a compromise between the amount of flux density that you want to maintain a certain value of inductance, for example, versus the amount of copper loss that you can tolerate in your windings, which will cause the temperature to increase, for example. Yeah. So why did I say I need Imax? So we need L minimum to choose a capacitor before we go back to the inductor. To choose a capacitor, the main parameters are what? Besides C minimum, I need V maximum, because this is going to do what? This is where the breakdown voltage of my insulator between the two, or the dielectric between the two plates, will fail. The dielectric material that is insulating the two charged plates in the capacitor will fail at a certain maximum voltage. What else is important for capacitor selection? We said it's something that's affecting the temperature, the lifetime. That's what? No, ESR is not, it's something that you will get based on the capacitor that you select. But how do you select the capacitor? Remember for the switches, what did we say? For the switches, it was V, for the diodes and switches. What were the two most important parameters? Vmax, the voltage across the diodes or switch, right? And then, what was the other parameter? We went to the manufacturer's website and we chose based on two parameters initially, right? What was the other parameter? No, max switching frequency is a byproduct as well. It's something that you filter on later. Remember, we chose two parameters, and then we were left with a set of switches. The set of switches had different rise times and fall times, had different RDS-ons or turn-on resistances. They had different other characteristics. But you had to first filter a first set of components that you were going to start looking at in more detail. So that it depends on, in the switch, it was maximum voltage because of the breakdown of the switch's insulation, as well as the average current. Remember? We said average current causes heat. Right? Average current is what's going to cause heat. So you have a switching current waveform. Current in the switch looks like this. So I will calculate this average current because it's an indication of how much heat that the switch can, that's going to be dissipated in the switch. Right? The power loss in the switch is the voltage times the current. The voltage across the switch and the current through the switch. So it's the average value of current through the switch that's going to cause the temperature to rise. Right? So these were the two parameters for switches and diodes that we started with. Capacitors, we have to first choose the minimum value of capacitance, which considers ESR. Okay, it considers ESR. And then we have to do what? Of course, the other main parameter is Vmax, because it's going to dictate the breakdown voltage of the dielectric material. Right? And then what's the other main parameter? Something that causes heat, temperature. Again, all electrical components, they can, if you cool them enough, they can withstand almost infinite temperature, which is why we have superconducting material. Right? Superconducting materials are materials that, they are materials that don't dissipate any losses. So you can push infinite amount of current through these theoretically speaking, infinite amount of current through these superconducting materials because they would never get hot. Right? So it's the other main parameter would be here ripple current. RMS ripple current. Because this will dictate the I squared R loss, IRMS squared R in the capacitor, which are the ESR R. Right? This is what causes heat. This is what causes heat in the capacitor. Right? So these two parameters, Vmax and IRMS, are what's important for capacitor selection. How about inductor selection? Definitely we have to get the L minimum, and then we work above that if we want to. And then what else? Something that is related to heat and something that's related to the physical component itself. So here it was a dielectric breakdown voltage. Here it was the dielectric breakdown voltage. This was heat. This was heat. So here, what is the physical limitation that I have in an inductor? Is it a dielectric? No. I have a certain amount of cross-sectional area that I cannot push more flux through, right? So what is the important parameter? It's maximum current, because maximum current is what dictates maximum flux, right? So maximum current is one parameter. That's something related to the physical component itself. Then there's another parameter, always related to heat. What is it? Again, inductor is a set of coils that have a certain resistance. So it's definitely what? The losses in this resistor. So what the losses in this resistor are dictated by the RMS current. Right? It's IR squared. I squared R, sorry. IRMS squared times this resistance will dictate the heat in the inductor. Yes? No? It's simple, guys. Like it's minimum value of the component itself, plus something related to the physical device. In the capacitor, it's the breakdown voltage of the dielectric. In the inductor, it's the maximum amount of flux lines that you can push to the core. So one will definitely then be Vmax, which dictates the amount of voltage that will break down the dielectric. The other one will be Imax, which is the peak current that will cause peak flux to flow into the core. Right? So you want to limit that to a certain value. So you will select an inductor, you go in and you select the inductor minimum value of inductance. And then you make sure that you're satisfying the I maximum, the maximum flux that you can push to the core. And so from that perspective, you actually selected the core, similar to selecting a core, right? But then you also have to select a wire, right? So selecting a wire will depend on the amount of loss. But not all wires can fit in any core, right? Because if you look for our transformer, for example, we cannot put a wire that's this big in diameter around the core that with a certain core window, right? You cannot, right? So there is a certain range or a number of wires or types of wires that you can use on a certain size of inductor core, for example, right? So this is how you would down select from your inductors, capacitors, and switches. So everybody's okay with that? So we can calculate the C minimum, L minimum, the voltage across the switch, and the current through the switch. No problem. But then how do you go and buy and select the real one? This is how you do it. Okay? So this is what this slide says. You know, the inductor wire has to be rated for the RMS current, right? This is the heat component I'm talking about in the inductor. Inductor core should not saturate at the peak current. That's why you select it based on peak current and RMS current, right? For inductors. Capacitors, you select it based on peak voltage because that's the voltage that will break down the dielectric of the insulation of the dielectric between the two plates or between the two sheets. And then you also have to base it on capacitor RMS current because we have AC current flowing through the capacitor, and that current will cause dissipation of loss current to dissipate in that resistor. So you have to consider that as well. Yeah. And then we talked about the effect of switching frequency. You know, increased switching frequency, the size of capacitors and inductors will be less. Why? Because the size of capacitors and inductors is proportional to, for the capacitor, the area under the current curve. If you increase switching frequency, that area decreases. Inductor, proportional to the area under the voltage curve. Increase switching frequency, that area will decrease at the same duty ratio. Right? So hopefully that is good. This 500 kilohertz, forget about this. It doesn't make too much sense. This is very dependent on the switch that you select, right? You know, the switching frequency is something that's dependent on, we saw last time, rise times and fall times of switches will dictate. I mean, you want to do it as fast as you can. You want to switch as high a frequency as you can. But you're limited by rise times and fall times, and you're limited by your switching losses, which we will talk about later today, hopefully. We talked about synchronous rectification, and I mentioned why people sometimes would replace, you know, a simple diode with a synchronous rectifier. So they would actually call this combination of MOSFET and diode a synchronous rectifier, where they would operate this MOSFET as a diode. So they operate it in parallel with it. So as soon as you turn off the MOSFET, the diode picks up the inductor current. But as soon as the diode starts picking up the inductor current, you have enough time to turn on the MOSFET. You turn on the MOSFET has a lower resistance, or if you calculate for the same value of current flowing through the MOSFET and the diode will have forward voltage of maybe 1.2, 1.5 volts. So this is like a voltage that's opposing the current flow of 1.5 volts versus this is a MOSFET with, I don't know, 10, 15 milliohm RDS on. The voltage drop across that's going to oppose the current will be a lot less than the diode. So current will prefer to flow in the MOSFET. Right? And if it flows in the MOSFET, then you have a lot less losses. So that's synchronous rectification. And some people, I mean, this is something that's very common now in power supplies. Of course, the drawback is what? This MOSFET is an active device. You actually have to turn it on and turn it off. So you have to have a gate drive circuit along with that. Right? So it's more complicated circuitry, so more expensive circuitry. But you're willing to put more expensive circuitry at the expense of improving your efficiency. That's your call. Right? It's load or a spec that you want to live with. Yeah. So that was a step down converter. We spent a lot of time on that, so hopefully it's clear, and we're going to go through these ones in next two faster ones. Yeah. So the step up converter is very similar to the step down converter. So actually, if I let me draw them next to each other, and you will see how similar they are. I will draw them. Let me draw. I'm just drawing it a little different. So this is the step down converter that we just finished. Right? I didn't change anything here. This is the step down converter. Come on, here. Right, I have a switch and a diode, and then the inductor and capacitor and the output resistance, right? So that's what I drew here. Okay, that's what I have here. I will draw now the step, so this is the buck or step down, or buck converter. Right, I'll draw the step up converter, but let me do this. I'll draw this the same. Everything's the same, right? Correct? But I will put my input power supply here. I'll put my load here. And for fun, I will add just one capacitor, just for fun. But this is, you can consider this part of the load for now. So did anything change? Nothing changed. So it's basically the topology is very similar, except that you switch the position of the load and the source. Yeah, right. So what's happening? Let's go back to the waveforms quickly. So what was happening in the buck converter, in the step down converter, the buck converter, when the device is on, what was the voltage here? When this switch is on, this diode is off. So what was the voltage here at this VP voltage? Exactly, it's VDC when the switch is on, and then when the switch is off, the diode is on for continuous conduction modes, and the output and the voltage here will be 0. So let's do this here. So when the switch is on, what's happening? Actually, let's do the. Let's do when the switch is on. Yes, when the switch is on. What's the voltage between these two nodes? Switch is on, diode is off. To less confuse you, you don't need this here. You can, you may need it, but I mean, it's not critical yet. May help to make things easier. When the diode is off and the switch is on, what is the voltage here? Again, this is a inductor is what for DC? Short circuit, right? So when the switch is on, I have a circuit that's composed of this, and the output. Diode is off. So what's the voltage here? The voltage here is what? What do you say? So I have an input voltage here. So this is the circuit now. I have the source. This is a short circuit. Inductor is short circuit. This is a closed switch, so it's a short circuit. And I have my output here. So what's my voltage here? Source voltage, right? So same. So this is here the source voltage. Here, same thing. I have source voltage. On this side, inductor. Source voltage, and when the diode is on, I have what voltage here? 0. Same exact waveform. right? So now comes the interesting part. Here was Vs, right? This voltage here has an average value of Vs, correct? And in the step down converter, I was taking this Vs, chopping it up to create a lower average value, right? So this waveform has an average value here. That is what? This is average value of Vp, waveform. It is equal to what? The duty ratio that we've selected, right? Remember the average value of any square waveform is equal to the duty ratio times its peak value, which is Vs, right? So that's the transfer function of the buck converter, right? V output here is equal to Vs times D, remember? So now how is this thing operating? Forget about what you have here, and forget about what you have here as a load or a source. Okay, forget about them, right? If this is the waveform here, this is the waveform here, right? And this is the waveform here, right? So forget about what you have here as well. Forget about what you have here. So what do you expect to get on this side? What do you expect to see here? From what voltage waveform do you expect to see here? This now is identical to this. Right? So what waveform do you expect to see here? Average value of this waveform. Come on, guys. Come on. This is right. This is the I mean, this is same two inductors, and this is the voltage here. So what do you expect the voltage here to be like? Same as this, right? So it will be what? It will be a voltage here that in this case is going to be equal to V input. In this case, it's going to be input is equal to actually this one here. I should have. This is a bit. This is okay. Forget about this drawing. But it should be equal to V input. This waveform, it has an average. This is a waveform that's taking this voltage. Sorry. Do we agree that these two circuits are identical? These parts of the circuits are identical. Then the peak value of the duty cycle here is what? The peak value here is actually this voltage. Let me call this, in this case it's called V output, right? So here the peak value is V output, and the average value is what? No, if it's a 50% duty cycle, yes, but no. If it's a average value of this square waveform is what? Is the peak value of the waveform multiplied by the duty ratio of the switch, right? So V input here happens to be duty ratio times V output, right? That's because of this waveform here. V output here is what you see on this terminal, right? Exactly like here, right? So it's the same. I have this same switch and diode, I have a voltage here, it's called V output. Voltage here, it's called what? Vs. Just happens to be called Vs. What do I see here? When this switch is on, I see this voltage, which is Vs. When this switch is on, I see this voltage, which is V output. Right? When the diode is on, I see 0 here. When this diode is on, I see 0 here. The average value of this waveform is V input. The average value of this waveform is V output. Okay, so what did I do? Here, I took this Vs, and the output voltage is a portion of Vs that's based on the duty cycle. Right? Here, it's the opposite. My input voltage is being stepped up to V output. Right? Or my output voltage here is being stepped down to V input, right? So here I'm taking this lower voltage and stepping it up to a certain V output. Here I'm taking my input voltage, which is high on the left-hand side, and stepping it down to a certain V output. So they're identical circuitry. We'll go to the waveforms, but I just wanted to show you that they're actually identical. So the waveforms, you will expect to see very similar waveforms, yeah. So let's go through the way that they do it in the textbook, and then we can draw the equation, the waveforms, the way that I like to do it, yeah. So here we'll start doing the same thing. We will, again, close the switch and open the switch, and then look at the condition of the circuit with the switch closed and the switch open, and then diode closed and diode open, and look at the voltage across the inductor. Same thing, we look at the voltage across the inductor when the switch is closed, voltage across the inductor when the switch is open, and then we will use that to calculate the ripple current when the switch is closed, which is open. The ripple current is always starting and ending at the same point, so we will add the two ripple currents and they will be equal to 0. Same process we did before. So here, this is the circuitry. This is a circuit. This is the buck converter. We're at the boost converter now. The assumptions are the same as well. We're operating in steady state, and the switching period is t, and the switch is closed for a period of time dt and open for 1 minus d times t. Inductor current is continuous in this case. The capacitor is very large, and the output voltage is held constant at the output at V output. Okay, and the components are ideal. So all of the same assumptions here. And then we'll close the switch. So the switch is here, and the diode is here. So we'll close the switch and open up the diode and look at the voltage across the inductor. The voltage across the inductor. One side is what? Is Vs. The other side is 0. So the VL is equal to Vs, which is equal to L di by dt. We rewrite di as the current ripple, and dt as the period of time when the switch is on, because the switch is closed. Switch is closed for a period of time dt, and this is your ripple current spec, or ripple current, right? So this I can rewrite now ripple current in terms of my variables, the rest of the variables. So this is the ripple current when the switch is closed. I do the same thing for when the switch is open. I calculate VL. VL in this case is equal to Vs minus V output, right? So VL is equal to Vs minus V output is equal to L di by dt. I find an equation in terms of delta I, and the time when the switch is open is equal to 1 minus d times t, right? So I find the equation for delta I when the switch is open. Now I know that I'm operating in steady state. So since I'm operating in steady state, inductor current will go up. This is my delta I when the switch is closed. Then it will always go down to the same point. I always have a periodic waveform that starts at the same point. So delta I going up plus delta I going down, or when the switch is closed and the switch is open, the sum is 0. I end up at the same position, right? So there's no delta I after. When the switch, I have delta I when the switch is open, a delta I when the switch is closed. What is the total delta I that changed? 0, right? So I have delta I when the switch is open. That was calculated from here, and then I do the same thing. I add the two delta I's to find my voltage transfer function. So add them up and simplify the equations. I end up with a relationship between V output and Vs equal to this. Okay, how? Again, look at what is the maximum. What is the minimum value of output that I have? This is the step-up converter. Now, what's the minimum value of output? Minimum value of output. No, this is your equation, right? This is your equation. Output voltage, minimum value of output voltage. Minimum value of output voltage. Let's redraw the waveform, the circuit I did, right? So we have our circuit looks like. Oh. I think I did a mistake on the previous slide. We have to switch the place of the diode and the MOSFET. I'll show you why anyway. This is my output. This is a step-up converter. Okay. So what is the minimum value of my output voltage? Remember, the output voltage equation is V input over 1 minus D. This is V input. Here, this is V input over 1 minus D. So what's the minimum value? D can range between what and what? 0 to 1. So put these two extremes in there. So if it's 0, V output is equal to V input. How about if it's 1? V output is equal to? Exactly. Okay? Yeah, I'm sorry, I left the switches exactly the same. That was wrong. We have to flip the diode and the switch in the previous drawing when I draw them on top of each other. The waveform won't change. At the end of the day, what does the waveform here look like? Right, we were drawing the waveforms here and drawing the waveform here. The waveform here, I want it to be what? I would like this to be an output voltage that is ripple free or has some low ripple content, and that's why I will add eventually a capacitor here, right? And then here the input voltage is this V input, nice flat DC, and here the waveform when the switch is on, it's 0, and when the switch is off, when the switch is off, it's V output or V input, right? It's when the switch is off, the diode is on. When the diode is on, it's V output. Assuming that because the transient, they will keep the effect of the inductance in there, right? So when the switch is on, it's 0, and when the switch is off, the voltage is V output. V output 0, V output 0, V output 0. So the waveform doesn't change. The waveform, the values that I have here doesn't change, and the average value of this is V input, right? So the average value of this waveform, which is what? Is this D or 1 minus D times V output? Remember, when the switch is on, it was 0. When it was off, it was V output. So what's the average value of this square waveform? It's the peak value times the duty ratio of that peak value. That peak value is occurring for the 1 minus D period, right? Guys, this is important. Do you agree that this average value of this waveform is 1 minus D times V output? And that is equal to V input. Okay, let me go back to draw them again. I have to make sure this is drilled into you, okay? It's for the buck converter. Okay, this is without any of the equations, right? For the buck converter, I have my source, I have my switch, I have my diode, inductor, output capacitance, and output resistance. This is for my buck converter. For my boost converter, I said I have to switch the MOSFET and diode, but here I will add my load, here my inductor, my input source. Does not matter if I put the capacitor here or not. I will justify that sometimes we need it actually. I will justify that to you. And we can add a capacitor here and we can add a capacitor here. Does not really matter. We can size it, right? If there's ripple current or if there's ripple voltage, then there's a need to put a capacitor. And I'll prove to you that there's always ripple voltage in this case. But regardless, now let's see what's happening to this. I want to draw this waveform. VP1. What does VP1 look like? This is VS. This is VS, and this is V output, and this is V output. Okay, what does VP look like for the buck converter? When the switch is on, let's start with always when the switch is on, right? When the switch is on, I have Vs at this point, right? And this is my ground or reference, right? So when the switch is on, Vp1 is equal to Vs. And when the switch is off, and the diode is on, so this is 0. Vp1 is 0. Diode's on, 0. This is happening when the switch is on. So this is time period dt, right? And this is what? This here is time period 1 minus d times t, right? How about for the boost converter? What is Vp1? Again, when the switch is on. When the switch is on, what's the output here? What is Vp? Let's call this Vp2. What's Vp2? 0. And when the switch is off, diode is on, and the voltage Vp2 is equal to V output. So it's 0 initially, and then V output. 0, and then V output. So what is the period or the time for this being on? No, it's not. It's 1 minus d times t, right? So this has a peak value of V output. This has a peak value of Vs. So on the other side of the inductor, we said that the inductors, the AC component of this voltage will be placed across the inductor, will drop across the inductor. And then the rest, the average will be here. So the average value of this waveform is what? Again, this is a square waveform. What's the average value of any square waveform? Peak value multiplied by the duty ratio. So peak value is Vs, multiplied by the duty ratio is dt. Or d, it's duty ratio, it's not time. Right? So it's Vs times d. This average value is what's going to appear here. In this case, it's equal to V output. Do we agree? Yes? How about in this case? Again, this waveform has an average value. This average value is what's going to appear here. So this average value now is going to appear here, and that's going to be equal to Vs, right? I only have an average value. I only have a DC source here. So this average value of this waveform is what? Again, it's a square waveform. What's the average value of any square waveform with a duty ratio? It's the peak value multiplied by the duty ratio. So it's V output times 1 minus D. That is the average value of this waveform. That is equal to Vs, because the AC component will be across this inductor. The rest is going to be seen on the other side of the inductor. Right? So Vs is equal to V output times 1 minus D. Here, V output is equal to Vs times D. Did I have to go through the equations here? So the transfer function that they came up with here is, V output is equal to Vs over 1 minus D. You don't have to go through the equations. These past 2 slides of equations, you don't have to if you understand the circuit and the waveforms, right? So, but if you have trouble with that, and the equations are there, right? So it's anyway. So what's the minimum value of V output again? We said the minimum value of V output for the boost converter is what? Again, D is 0 or 1. The minimum value is going to be what? Vs. And it makes sense. The minimum value is equal to Vs when D is 0, right? Right? D is 0. V output is equal to Vs. D is 0 means this switch is open. If this switch is open all the time, right, the equivalent circuit looks like, that means the diode is on, right? It means the equivalent circuit would look like this, right? And V output is equal to V input, right? That's the equivalent circuit if D is off forever and diode is on forever, right? So that's the equivalent circuit in this case. How about when D is 1? D is 1, also these 0 or 1 don't happen, right? Because you can, if D is 0, that means the circuit looks like this. But if the circuit looks like this, then eventually and always, if it doesn't change mode, then this inductor really is not doing anything. and the inductor will be a short circuit, and I just have this. There's no need to have this circuit anyway, right? There's no need for the circuit. And same thing when D is what? 1. If D is 1, I have the switch on all the time. If the switch is on all the time, then the equivalent circuit looks like this, right? The switch is on all the time. The circuit looks like, what is the output voltage? The output, this is 0, so it's something over 0. It's an infinite value of voltage, right? So does it make sense? Infinite value. Where does it come from? That the fact that this is a source with an infinite amount of infinite amount of current. This is a source with infinite amount of current, and this is a inductor with a voltage that has a voltage drop across it due to current flowing. You're putting infinite current because of the short circuit that you placed, and you will have an infinite voltage, theoretically speaking, yeah. Right? But does this happen in practice? No, because this typically has a certain value of resistance, and this typically has a source limit. I mean, a battery is rated for a certain amount of current that it can push out. You cannot withdraw infinite amount of current from a battery. A battery has an equivalent circuit that typically looks like an ideal source with a resistance in series. So regardless of putting a short circuit in here, you will be limited by the amount of current due to the ideal source. There is a limit, right? Okay, so what was I trying to say? So does everybody see how this operates? How the boost converter operates? So when the MOSFET is on, what's happening? When the MOSFET is on, the circuit looks like this, right? I have a source, an inductor, and a short circuit, right? What's happening to the inductor? I'm charging the inductor, right? I'm pushing current through the inductor. I'm building up the magnetic field around the inductor during this mode, right? So the longer I keep the switch on, the longer I'm connecting my source to my inductor, the longer or the more energy I'm storing in the inductor. That's what's happening, right? This delta lambda, remember, delta lambda is equal to the area under the inductor voltage curve, right? So if I'm placing a positive voltage across that inductor for a long period of time, right? So I'm placing a positive voltage V input across my inductor. The more I increase this, what's going to happen to my inductor current? VL is equal to L di by dt. Inductor current is equal to 1 over L integral of VL. Right? So the more I keep this on, the more I will be able to push current into my inductor. Inductor energy storage is equal to what? Half Li squared. If I increase I can store more energy in the inductor. How can I increase I? I maintain a duty ratio, or maintain this voltage, meaning maintain the switch on, meaning increase my duty ratio of the switch for a longer period of time. Of course, there's a limit, right? There's a limit of this I max that we talked about before, right? But this is the principle, right? So you're storing energy in the inductor initially, and then what happens? I stored energy in my inductor. I stored energy in my inductor when the switch is closed, and then I open the switch. If I open the switch, my source current as well, remember this is now an inductor with initial current through it, right? So you have two sources now in your circuit, so it's like superposition, right? So that's where the boosting feature comes from, right? You have a superposition. You've created an additional source that you've put now into the circuit. That source you've charged by closing the switch. And now when you open the switch, this source becomes an additional source into your input, right? This is like both of them are now your input to the circuit, right? So now this is an additional source. From superposition, it will create an output voltage. This one was creating an output voltage if you put it there by itself, right? So now both of them are being added to your output. The energy from your source as well as the energy from the energy stored in the inductor. That's where the boosting capability comes from. Okay? Okay, so we came up with this. And I showed you how to come up with this without the equations, right? So what is the maximum value of the output? It's infinite, right? Okay, it's infinite. We said it's infinite only if I don't have losses in place, right? If I have losses in place, then it does not become infinite. Because what happens when you have losses in place? When, let's say you have this inductor has a resistance in series, right? What's going to happen to the output voltage? What happens to inductor current? Let's do this. What happens to inductor current average value when I increase duty ratio? Here. We said this is what's happening to the inductor current. If I increase my duty ratio, inductor current will keep increasing, right? But assume I have a certain current ripple, for a certain value of current ripple. The higher the duty ratio, what will happen to my inductor current average value? If I keep increasing my duty ratio, meaning storing more energy in there, and I have a certain ripple, I'm maintaining a certain ripple current. What's going to happen to the average value? Yeah, look. This is inductor current, for example, certain ripple. Right? If you increase your duty ratio, what will happen? This has an average value. This has a certain average value. Average value of inductor current. Look at the average value. Look at the DC characteristics of this circuit. Okay, what is the average value of the inductor current equal to in this case? Average value of the inductor current. It's going to flow again. Average means DC, right? The average value of inductor current will flow in the circuit. The DC equivalent circuit of this system looks like what? A source, an inductor, which is a short circuit. So I'm increasing the average value here. This capacitor is an open circuit. That means the average value of the load, average value of inductor current is equal to the average value of the load current. Right? So increasing the duty ratio would increase the average value of load current because I'm able to store more. So if I'm able to store more energy in my inductor, that means I'm able to boost my output voltage. If I'm able to boost my output voltage to higher values, given the same value of resistance, what does that mean? Higher voltage, same resistance, it means higher current, right? So I'm able to, if I store more energy in the inductor, I'm able to increase the output voltage. If I increase the output voltage for the same value of resistance, that means I am increasing the average value of current. This average value of current flowing in my load is also the same average value of current flowing through my inductor. Do we agree or not? No?
What's your question about increasing resistance?
Yeah, I'm now saying if I put a resistance here in series, okay, and I increased my duty ratio. If I increase my duty ratio, we agreed that if I increase my duty ratio, I'm storing more energy. If I'm storing more energy, I'm able to boost the voltage on my output. If I'm able to boost the voltage on my output for the same value of resistance, that means my average value of current has increased, which happens to be the same average value of current through my inductor. If I put a resistance here, that resistance is also seeing a higher average value of current as well. So higher value of current to the resistor means higher voltage drop. Right? So the more you increase duty ratio, so I was trying to say this. We said that the output voltage in a boost converter is equal to the input voltage over 1 minus D. Draw this. Draw V output versus duty ratio. At duty ratio of 0, what is V output? Vs. At duty ratio of 1, what is V output? Exactly. Okay? This is assuming a lossless circuit. Now I said that I don't have a lossless circuit. I considered the inductor resistance, for example. right? I have an inductor resistance, and I have my switch here, and my diode here, and this is my output load, right? Now, I said that if I'm able, before I put this resistance, what was happening? Anytime I increased my duty ratio, meaning I kept the switch on for a longer period of time, I was storing more energy in the inductor. I stored more energy in the inductor. That means when I turned off the switch and allowed this energy now to flow from the inductor and my input voltage source to the output, I was able to boost my input, my output voltage, right? If I did not store any energy, meaning I kept the switch off, I kept the switch open all the time. If I kept the switch open all the time, what was happening? I was taking my input voltage and connecting it to my output, right? This is my equivalent circuit. Diode was on. I have my output capacitor, the resistor. This is a DC source. This is a short circuit. This is an open circuit. Right? So I'm connecting my input to my output. And that's why the minimum value is Vs. Minimum value of output voltage for duty ratio of 0 is Vs. Now I kept this switch on for a longer and longer period of time. What am I doing? I'm taking my input source, charging my inductance with energy. Then I open up the switch. After I open up the switch, the diode is on. The diode is connected. Why is the diode connected? Because there's inductor current flowing. Inductor current flowing, there's no path for it to flow in the switch, so it's going to have to flow through my diode. Right? So because it's going to flow through my diode, now it's like having a circuit with two sources in series that is connected to my output. Simply, that's what it is. You have two sources now connected to your output. You're adding this source plus this source to create the output voltage now. That's simply what you're doing, right? So this is increasing the output voltage across my load, meaning it's increasing my average current through my load. My average current through the load is also the average current here through my inductor, because capacitor is an open circuit for DC, right? So, which means that if I keep increasing my duty ratio, I keep increasing my average inductor current. If now I consider the value of this loss, anytime I keep increasing the value of current through this resistor, what happens to the voltage drop across the resistance? Increases, right? And it's in an opposite direction than your two sources. So now it's like having three sources, but two sources are summing up, and one is subtracting. That's what I was trying to say. Is it clear? So one is subtracting, and this one that's subtracting is subtracting more. The I squared R will increase more when the current increases more, right? It's small values of current. I squared is a small value, but it's a quadratic, right? At higher values of current, the I squared is a higher value. So what do you expect? So I expect at the beginning, when I have small values of current, meaning duty ratios are very small, that I will not see much of a difference, right? But then I expect that high values of duty ratio, that this effect of this subtractive effect of the resistance that's in series will become dominant. It will dominate. It will become very important at that point, and it will, instead of them being able to go to infinity, at some point, if I put an infinite amount of current through this resistor, right, then what's going to happen? If I put an infinite amount of current through this resistor, meaning this switch is on all the time. If this switch is on all the time, then this voltage drop across the resistor will almost be equal to the voltage at the input. So you will be canceling the effect of the input at all. You will not be able to charge your inductor. That's at an infinite amount of current, for example, which is theoretical. Yeah. So what you will end up seeing is, instead of this going up continuously to infinity, it will at some point do something like this. Right? So yes, you will be able to boost, to a certain value, but beyond that value, you're not going to be boosting anymore. The effect of the resistance will be reducing the voltage much more considerably because of the I squared effect. So I squared is increasing very fast, and it's going to not allow you to boost the voltage any further, right? So there's a point beyond which you cannot boost. That point is typically about 4 times the input, 4 to 5 times. Okay, so you should be able to boost from 10 volts to 40 volts, or from 10 volts to 50 volts. But can you boost from 10 volts to 100 volts? No, you can't. And that's why you had to use a transformer in your project. Okay? Because you could have used the boost converter to go from 12 volts to 180 volts, theoretically speaking. But that's assuming a lossless circuit. Okay? So that's the reason why you have this in your project here. So we'll stop here. I was hoping to finish more, but I hope at least it's clear. The idea of the boost converter and how it operates, I hope it's clear. Yeah.